Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. My name is LUQMAN bin ZAHID, and today I am going to present my undergraduate project titled Development of Low-Cost Braille Embosser for Tactile Graphics. I am supervised by Dr. ZARHAMDY bin MADYA. Here are the list of contents. Chapter 1 will be on Introduction, Problem Statement, Objectives and Scopes. Chapter 2 will be on Literature Review. Chapter 3 will highlight on methodology. Chapter 4 will showcase the results and the findings. Chapter 5 will conclude on the project that has been done. Chapter 1, Introduction. In 1821, Louis Braille invented the Braille coding system to help the visually impaired to read and write. The invention of this system is revolutionary, as prior to it, the blind could only read heavily embossed lettering. The invention of Braille transcribing system has significantly improved the reading and writing among the blind people, and literacy rates among the blind increases. Literacy rates among the blind soared from the invention of the Braille system to the 1960s, with almost 50% of blind school children able to read Braille in 1960. The slate and stylus are used by visually impaired persons to write Braille characters onto paper. It is the earliest transcription method known, and it was invented by Charles Bavier. Writing is accomplished by placing a piece of heavy paper in the slate, aligning it correctly and closing the slate. The pins in the back of the slate puncture or pinch the paper securely between the two halves of the slate. This tool is very portable, but prolonged use can result in fatigue of the user due to the force needed to emboss the Braille on heavy paper. Use of the slate and stylus is often seen as difficult, writing backward, and unnecessary. The standard and original Perkins Braille were invented by David Abraham in 1951. The Perkins Braille is a mechanical Braille that has 6 keys to emboss Braille dots on paper, and it also has additional keys such as the space bar, the backspace key, and line spacing keys. The weight is about 4.7 kg with a dimensions of 37 cm long, 23 cm width, and 15 cm high. The user can type 25 lines with 42 Braille cells on 11-inch by 11.5-inch paper. The standard Perkins Braille costs around $750 US. The average force needed to emboss the Braille character on a standard Braille character of 140 GSM thickness is 9.38 Newton. Other than the standard Perkins Braille, there are also the basic D V5 Braille Embosser, which is a small and portable Braille printer. It uses fan-folded paper, which is the most commonly used paper style for Braille embossers. The basic D is also stable and capable of a continuous Braille embossing. It supports the use of Braille app printing software. It has a net weight of around 7.6 kg. It has a price of around $3,695 US. The embossing speed is 100 characters per second. The measurements are in centimeters, 13 centimeters height, times 52 centimeters width, times 26 centimeters length. The forming method uses 13 hammers or anvils. Tactile graphics are in essence a series of dots formed on a piece of material that is meant to represent visual stimulation, such as pictures, but for the visually impaired. Oftentimes, important figures in science, technology, engineering, and mathematics are not readily available in a format in which the blind can access. A vast majority of mobility maps are made for individual users who wish to travel independently. A high school student who had recently moved to Ottawa, Canada, was given the map due to the fact that he wanted to learn on how to use the public transport system in Ottawa. It is interesting to note that the student successfully memorized the pattern of the street quickly. For the problem statement, the price point of basic D V5 in the market is quite expensive, with a price point of 16,100 ringgit Malaysia. The basic D V5 in the market is heavy for the visually impaired to carry around with a net weight of 7.6 kg. The objectives of this project is to develop a Braille embosser that utilizes a different forming method than the Braille embosser in the market to reduce costs needed to manufacture. The scopes for this project is study the concept of Braille embosser, design and develop the hardware for low-cost Braille embosser for tactile graphics. The testing on the quality of Braille dots formed on 3 paper thickness 140 GSM, 80 GSM and 70 GSM paper. Validate and evaluate the results of the performance of low-cost Braille embosser. Chapter 2 Literature Review. Chapter 3 Methodology. As you can see here, this is the overall project flowchart. It starts from the problem identification to the gathering of information to concept generation, in which 3 concepts will be generated: concept 1, concept 2 and concept 3, and then comes the evaluation of the concept, and last but not least, the finalizing of the design. Next is the product design specifications. Product design specifications highlights the criteria which needs to be met in designing a product or a process. The stages for all engineering design activities are also set by the document, thus ensuring the success of the design activities by making sure that all important factors are taken into considerations. Here is the function block of the printing mechanism. First is the translation of the text document to Braille G-code using translation software, and then the G-code will be sent to CNC controller software, which are GRBL software. X and Y axis stepper motor will align the paper to the printer head, and the printer head will start embossing the G-code. Next is the morphology chart. For the movement mechanism, it will use lead screw or rack and pinion. The actuator of embossing pin will be selected from 3 choices, which are solenoid, servo motor and linear actuator. The microcontroller will be either used from Arduino Uno or Raspberry Pi. The position of embossing pin will be placed statically or free roaming on the x-axis. As you can see from the 3 figures here are the 3 different concepts generated. As you can see here in the evaluation matrix, there are 7 different criteria. During the process of the evaluation, 3 other persons have been assigned in order to assist. As you can see here, the average marks for design 1, design 2, design 3 are presented, and we can see that the design 2 receives the highest average among the 3, and design 2 will be used into the PROF matrix as the data. After the evaluation matrix, all 3 of the designs will be subjected to PROF matrix, in which the design 2 receives the highest score in the evaluation matrix, and it will be used as a datum. They are compared by each other whether they are better than, worse than or similar with the datum design, in this case the design 2. In the case that the modified design is better than datum, then the new modified design will be used in the final concept. As you can see here that the design 2 is still the better design as compared to design 1 and design 3. Thus, design 2 will be finalized. Once the PROF evaluation matrix has been done, design 2 is chosen and it is finalized, and here we can see the SolidWorks drawing of the final design, which is the body frame of the low-cost Braille embosser. Engineering analysis is done to calculate the force created by servo motor arm through the actuated head onto the embossing pin. Using the formula of torque equal to force times length times sine theta, we can get the force of 8.825 Newton. Chapter 4 Results. As seen here in the left figure, the 3D SolidWorks drawing of the actuator head prototype, and in the right figure is the actual 3D printed actuator head prototype. The actuator head is driven by servo motor SG90 and is connected to the embossing pin. The method used to manufacture the actuator head is by using 3D printing using ABS. Here we can see the assembled low-cost Braille embosser with the actuator head attached to it. Configuration of paper to be embossed. The paper are clipped onto the paper holder made by using stainless steel and clipped by using paper clip. This is done to ensure that the surface of the paper are static and are stiff enough to be embossed. In this video, it will show the actual printing mechanisms done on a piece of A4 70 GSM paper. The shape that is being printed is a square shape. We can see here the tactile graphics form on 3 different paper thickness, which are 140 GSM, 80 GSM and 70 GSM. The area of shape form are in millimeters, 74 height times 74 width. The quality of tactile graphics form on the 140 GSM paper can be fitly seen. As for the 80 GSM paper, it can be seen clearly, and for the 70 GSM paper, the tactile graphics form can be seen the most clear. As for the stimulation of the raised dots to the fingertip, the 140 GSM are not that noticeable. For the 80 GSM are more noticeable when touched by fingertips compared to the 140 GSM. And for the 70 GSM, the raised dots are the most noticeable as compared to the other two. Cost analysis have been done on all the items needed to manufacture this low-cost Braille embosser. All items that make the body frame up till the smallest part, such as actuator head, is included in the cost analysis to get the accurate cost. The total cost required in producing the low-cost Braille embosser is 517 ringgit and 30 cents in Ringgit Malaysia, which is a lot more cheaper than the price of basic D V5, which is 16,100 ringgit. Weight analysis has been conducted on the assembled body frame of the low-cost Braille embosser with actuator head by placing it on top of a weighing scale. The total weight of the low-cost Braille embosser developed is 4.65 kg. The weight is considerably lighter than the weight of the basic D V5, which are the datum, which are 7.6 kg. The force produced by the servo motor, which is 8.825 Newton, is inadequate to produce a quality Braille dot on a piece of 140 GSM paper. The force produced by servo motor is enough to emboss successfully on 70 GSM and 80 GSM A4 paper. The Braille dots have some deformity on them, that some dots are not raised enough as compared to others due to misalignment of the servo motor arm pressing the embossing pin head. The quality of the 3D printed head actually also played a role, and it caused problems during the embossing process, as the surface of the 3D printed head of actuator head is not smooth, and the slide mechanism of actuator head is affected, resulting in a not efficient embossing process. Chapter 5. Conclusion. Although there are some problems faced during the continuation of this project, mainly the pandemic that spread globally, COVID-19, this project has been successfully completed. The objectives and the scope of this project has been achieved, although the performance of the low-cost Braille embosser is not as good as now as the one in the market due to cost restrictions. Recommendations for future improvement are a stronger servo motor that have larger torque should be used so that thicker paper can be embossed. Creation of an automated paper feeder to eliminate the need of manual paper configuration of the embossing paper. Also, the track for movement of the X and Y axis needs to be redesigned to make the embossing process smoother. Last but not least, the alignment of the servo motor arm to actuator head needs to be directly perpendicular so that the pin head can form dots on the paper better. Here are the references used to make the slide presentation. Thank you for your time and your cooperation.